Well, first off, I want to introduce myself, although Nikos already did. Um, my name is Josep. I'm the team lead of the PAPI team. Um, I'll be teaching at the DAPS track with my colleagues, Victor and Carlo. But I will also be teaching here for the fundamentals. Uh, yeah, I've been in the ecosystem since 2021, and I was at the point like I did the PBA edition in Singapore. So maybe in a couple of years, some of you will be teaching as well. This is just to say that we're always learning, and at some point we start learning, we get hooked into this, we learn more, and sometimes we end up teaching ourselves. So. Okay, what are we going to be learning today? We're going to be learning scale. First off, I want to know, I want to get a sense of how many of you know a little bit what this is about. So does this term scale or scale encoding and decoding ring a bell to any of you? Raise your hand. Okay, so a few of you already are more or less familiar with scale. Okay, it's also very important that for the duration of this session, if at some point in time I'm going too fast, I'm explaining something in a way that it's confusing or whatever, raise your hand, we'll go over it. It's a lot more important that you learn than me just like going through the slides like nothing happened, yeah? Okay, so what is scale? We'll get into that in a moment. Before we go there, we're going to talk about serialization. Serialization is the process of translating a data structure or an object in any programming language into a format that it can be stored, right? Like, so if you use JavaScript, like, and you do JSON stringify, that is serializing in a very naive way, but it's actually serializing, right? It's serializing like whatever JavaScript object or stuff that you have into a string, and then you do JavaScript parse, and then you deserialize it, right? That's a trivial way of serializing. There are different kinds of serialization, right? Like there is self-describing and non-self-describing. The example that I gave you before about like the JavaScript JSON, that one is self-describing because when you deserialize it, well, when you are serializing meta information, not only the actual values, but also like how these data structures are being presented, right? Then another concept that is important to remember is codecs. We're going to be talking about codecs all the time. In reality, a codec, the only thing that a codec is the junction of two things, of an encoder and a decoder. An encoder is you take some sort of type, you encode it into the kind of output that you want, normally binary data, and a decoder takes that output and it makes into the input. So a codec is just a data structure, if you want, that consists in two functions, one for encoding and one for decoding. And if you think about the types, the type of the input of the encoder is the same as the type of the output of the decoder. Yeah? Okay. We're going to do a quick recap on binary data because it's important that we're all on the same page on these things. So first off, what is a byte? Who can tell me what is a byte? Who knows what a byte is? I know it can seem very basic. Okay, so what is it? Don't worry, just yell. It's 8 bits. Why? Why 8 bits? It's true. Like he said, it's 8 bits. In 99.9% of computer architectures, it is 8 bits. Why is it? Why 8 bits of all numbers? Why not 6? Why not 4? Why not 3?
That's a good question. I actually never thought about that. Probably out of convenience.
It's 8 bits, as we just discussed. It's because it's the smallest addressable unit in of memory, right? So when we try to access a position in memory in a computer, like again, yeah, in almost all architectures, that's the smallest unit of memory. So there is no way. Like, sorry, yes.
That still doesn't answer like why it's 8.
Oh, no, what I was trying to explain is that why it's 8, because that's the way that the architectures have been done. Because it started with 8 bits, but yes, but the point that I'm trying to convey here is that the reason why we work with bytes, and the reason why this is like kind of it's like we're not working directly with like just zeros and ones, is because when we try to access the memory of a computer, it always gives us a chunk of 8 bits, right? Which is a byte at minimum, right? So when we're manipulating data, we're manipulating it in a byte, not in something smaller than that. Yeah. And something that is going to be very useful is the hexadecimal representation, right? So I guess everyone is more or less familiar with hexadecimal values and hexadecimal representation. We're going to just go over it again. Hexadecimal representation is a base 16 number representation. As you know, we, generally speaking, we normally use base 10 numbers, right? There are only 1, 0 types of people, the ones that understand binary and the ones that doesn't. You get that, Joe? So what I mean here is that there are many different bases, right? Like we use 10 probably because we have 10 fingers. Like if we had 12 fingers, we'll have been using base 12, which is vastly superior actually, but that's not the point. The point is that base 16 is very useful for dealing with binary data precisely because the properties that it has, which we'll see in a moment. So base 16 is, we are using 16 symbols from 0 to F, right? It's worth noting that whenever we see 0x, that's a very common notation that expresses that what comes after is expressed in base 16, okay? So the reason why base 16 is very useful for dealing with binary data, especially with bytes, is because each symbol accounts for what is called a nibble, which is 4 bits, right? That way, whenever we are trying to get, like this is a byte, right? And these are like inside the byte, we can split it in 2 parts, like one nibble, which is 4 bits, and the other nibble, which are the other 4 bits. So when we see 6A, we know that there is a byte, right? In which the first 4 bits, right, are a 6, and the other ones are a 10, right? Like this is, as you can see, this is 2 and this is 8, so altogether do 10, and in hexadecimal that's an A, right? Like, so hexadecimal is a very useful notation for visualizing what are the values inside this byte. Is that clear enough? Like, do you understand why we use very often when we're dealing with binary data hexadecimal? We could be using base 64, which makes things more compressed, but then we wouldn't be able to distinguish in the first character whether that's 1 byte or 2, right? Okay, so now that we have done a recap of like the most basic stuff, let's go directly into scale. Scale stands for simple, concatenated, aggregate. It's the same, just like they were trying to make it sound fancier because still it wouldn't sound so good. And little endian. Who knows what little endian is? Okay. Don't worry about it. I will explain it in depth in a moment. I just wanted to get like a. Okay, so a scale is designed for high performance, copy-free data encoding and decoding in resource-constrained environments, meaning that whenever we have to pick a method of serialization, we have to choose between different trade-offs, right? we could have something that is not so performant but really good for debugging, or we could have something that is highly performant but maybe not so that not so great for humans to decode, right? So scale has picked the path of being highly performant, right? And has also picked the path of being very succinct in the amount of memory that it takes. And it works really well in resource-constrained environments. So there's a question there?
Hi, it's Ben. Could you expand on the phrase copy-free data?
Yes. Actually, I'm going to do that just in a moment. I was going to do that now. So this has to do, I will expand on that later when I explain the properties of little endianness, but just so that you get an idea, what it means is that it's designed so that if you want to cast, for instance, you have U32, right? I'll expand later when we talk about little endianness, but basically using the same memory, if you want to cast it into a U8, you don't need to recopy it and reshuffle it. That's one of the advantages of using little endianness, but we'll get deeper later. I just wanted you to know that these are like basically the targets, right? Like when scale was designed, it's like what we want to avoid having to use too much memory and to do things as cheaply as possible when decoding this information, right? And also when juggling it around. So scale is non-self-describing, right? What means is that when you get like scale binary data, unless you know what it is that you're going to decode, you won't be able to decode it, right? Like unless you know the definitions of what you're looking at, you won't be able to decode it. As opposed to the silly example that I gave before, where you have like a stringified like JSON. Well, the stringified JSON is self-describing. You have in there like the name of each field and like whether this is an array or this is an object or this is a number or a Boolean value. When things are scale encoded, the one that's going to decode it needs to know what the definitions are. Otherwise, go figure what it means. Okay. Little endianness has some performance benefits, like free casting. Now, when we see little endianness, you'll see, and this is related to copy-free data encoding. You'll see what I mean. Indeed. Okay, so little endian. Little endian has to do with in which order we put the bytes, right? So if you see these two different stacks, these represent like memory addresses, right? So here we have byte 0, byte 1, byte 2, byte 3. Imagine this will be a good, this could be, for instance, U32, right? Like there are, or I32 or whatever. So imagine a U32. Does everyone know what a U32 is? Is an unsigned 32 number. So an unsigned 32 number is a number that takes 4 bytes, right? Now the question is, how do we put these bytes? In which order we put them? The least significant byte goes first or goes last. Well, depending in which order we choose, is going to be big endian or little endian. Let's see some examples. Okay. How do we encode the value 15? Like this 15, this is a decimal value. Like this is like 15. Okay. As a U32, right? How do we do it? Imagine that we want to do it big endian, right? So what would that be? Okay, there is someone who wants to. Big endian.
Hi, I'm Marcin. So the big endian will be like 0, 0, 0, 0, 0, 0, 5 F, I think.
Yes. So it will be zeros exactly. So we see like the order of the bytes of big endian. Here we have 15, yeah? And then we have, all these are padded because they're not being used. And then this one goes here, right? Like that's, for most people that write left to right, this kind of makes sense, right? Like, what about little endian? What would be little endian? Go
Okay,
for it.
so it will be 0F0000000.
Mhm. Yes, so it's 0F. One thing that I want you to note is that it's 0F. I'm not as smart as he is. So when I first learned about endianness, I assumed that it was going to be like a mirror. So I thought it was going to be F0. But it's not F0, it's 0F. Why? Because the bits inside the byte are left alone. Like endianness only applies to the bytes, right? The inside the byte, the bits are just placed however. Like and that's because really the computer, for the computer, like the byte is a black box. It's just like a bunch of zeros and ones, right? So just keep in mind that endianness, can be a little bit confusing when we see like things as binary data, as pure binary data, zeros and ones. Just keep in mind that endianness applies to bytes, not bits. Yeah? Is that clear? Does everyone understand how endianness works? Oh, so since we are here, just notice one thing. I think I'm going to explain that later, but like I feel like explaining it now. Imagine that you want to cast this value. It's a U32. Imagine that you want to cast it as a, you know that it's expressed as a U32, but because it comes from a system that is using U32s, but you know that this value is always going to be able to fit in 1 byte. So you want to cast it to a U8, right? Okay, so what do you do when you want to cast it as a U8 if you have a big endian? You have to basically copy all these, take these and put it in another place of memory to grab this. What happens with little endian? You can use the same address of memory because when you cast it, you're going to take just the 0F, so you don't need to recopy it. So that is, oh, shoot. Oh, sorry. Do you understand what that means? This is one of the little advantages of using little endian, which is like casting is kind of free. Oh, shoot. Okay. Gosh, I'm fat. All right. So yeah, what I was explaining is that when we cast it, we can use the same address in memory, just it's going to take until here, we'll need to recopy it. Here, if we try to cast it and we try to pass the same memory, the same memory address, it won't, that property doesn't apply. So you will need to recopy it, shuffle it, put it somewhere else and pass it. There are questions, so let's answer the questions. Yeah.
Spen, is there a way to, 2 questions. Is there a way to convert either from big endian to little endian and little endian to big endian? And if it's just focused on bytes, what happens in situations where we're trying to account for storage of bits? Maybe the next thing is like there's a bit, it's not complete bytes, or as the case may be. Are there scenarios like that?
So hold on, let's step back for a moment. Like, can we, so basically, can we convert something from little endian to big endian? Sure. Like, whenever you decide to see, like, normally you're working with binary data. Like, if you are working with typescript or whatever, you're going to be using uint array with a data view, whatever. If you do Rust, like, each language is going to give you different tools, basically, to access buffers of binary data and then express the binary data there however you want, right? So those are blobs of binary data. So you can definitely take some binary data that was encoded in little endian and then translate to big endian. Sure, you can do that. it has a cost. But yeah, you can like basically you can have in the same way that you have a U32 encoder, you can have one for little endian, one for big endian, and yeah, you can. Like basically you read it and then you put it. Yes. And the other question was, sorry?
Because the example we're considering, I don't know if it's unique to this example, it says how to encode the 15 decimal value. So I'm just looking at if there are scenarios where we're not dealing with bytes then, but we're dealing with bits. And if
I didn't understand, sorry.
so, are there scenarios where we're not dealing with bytes itself, but we're just dealing with bits itself?
No.
Okay.
Like the minimal unit of measure for binary data, as I explained before, is the byte, right? Sometimes, as we'll see later, we do what it's called. I don't want to confuse you, but like sometimes, like what you do is like inside the byte, you do what it's called bit boxing. Well, that's how I call it. I don't know what the proper term is, but like inside the byte, you express something more than just a number, and then you just look at the bits, and there is actually a really good case that's about to come that is part of scale. But for now, I'm just explaining endianness. Let's not get ahead of ourselves. There was another question.
Maybe I'm going a little too far, but is the reason that little endian is more useful is that you can easily find the extra zeros and wasted space? Or does using little endian make it any more efficient and more compressed?
Go ahead.
So with big endian, with the 6 zeros up front, I don't know if it's the compiler that has to identify it, but
So these 6 zeros, these are 3 bytes, yeah?
Yeah.
There are three empty bytes here, yes? And then
So
there's one. Yeah.
is it easier to identify the unused bytes by using little endian first for the machine?
But you're
Does that make
using
sense?
all the bytes. It's not such thing as unused bytes. It's a U32. Like you're using all the bytes. It's just like the value contained inside is just 15, but you're using all the bytes. It's a U32.
I see. So it's easier to read the little endian because the
No,
zero.
like little endian is a little bit more difficult to read for people because like I gave you 15, but when you see a number like bigger that has like other things here, it's a little bit confusing. While this one, it's like you just keep going, concatenating. So for humans, like little endian is a little bit confusing, but for computers, for programs, is more efficient basically because of the precasting that I explained. Oh shit! Is there a way to change this setting or?
Cool. Thank you.
Sorry. Sorry. I want to see myself again. I want to just. All right. Wait, did I answer your question? I'm not sure if I did. Yeah. Okay.
I can try to elaborate on the answer, if I can.
Okay. No, because there are other questions like.
But I don't have a question. I just want to elaborate why little endian could be easier to read. Like in big endian, you need to read this first three 3 bytes of zeros, and then you have the 15. But if you're expecting to read U32, like you're expecting there to be 15, you can just read 1 byte and skip the rest. Yeah, so that makes it easier to read because you don't need to read all of them to memory.
You think little endian is easier to read?
Like for the computers, like yeah.
All right, then there will be a just access later that we'll see if that's true. Okay, there were other questions.
I was just wondering, are there any benefits to using big endian?
Are there benefits of using big endian?
Yeah, just like maybe not in this case, but just in general.
Everything is about trade-offs. Yes, like so I'm sure like there must be a trade-off where like a big endian is a good option. Ethereum uses big endian.
I think, yeah, I'm building on that question. Is it primarily because of historical reasons that x86, ARM, and all these architectures use little endian, and it's only like Java or, I don't know, maybe?
No, I mean, like, the reality is that, like, another big reason why Scale uses little endian is because WASM, in general, by default, uses little endian. And as you know, as you probably know, Polkadot until recently, well, even today, it compiles to WASM. Later, it will compile to PBM, but the PBM that it will compile, it also is going to be little endian based. But yeah, like there was quite a bit of research, and And when they developed WASM, they realized that for the use case of WASM, little endian was a lot more powerful. Yeah. But yeah, like it's like there are trade-offs, right? Like again, like in Ethereum, I don't want to talk too much, but like the minimum word is 256. So it's like waste of memory nonstop, but like the pagination is the same. So there are trade-offs. Like yeah. Anyways, I don't want to. Yeah. Let's keep going. Okay. So now we'll look at the scale basic primitives, right? Like these are the most easy simple types that you can imagine, and then we'll explain like the most complex ones, right? So unsigned numbers, right? Sorry, these are U8 to U256. I'm not sure if they are considering adding more than that, but like for now, let's say that scale supports from U8 to U266. There's another primitive that allows us to have even larger numbers, but we'll get there later. So for instance, in these examples, this is how 20 is represented, right? Like this is a U8. It takes one byte. This is a U16, takes 2 bytes. As you can, and here you can again see the free casting, right? That comes with it because it's the same, just adding 2 zeros here, and then 256. This is a little bit confusing, right? Because like normally you will see these, right? And you'll be like, oh, that's 1. No, that's 256, right? Because 255 is FF, but now when we add one more, it's 1 in the next byte, so it becomes like this. That's why I said that little endian is a little bit difficult for humans to. It's not difficult. It's unintuitive at first. Once you got used to it, like you start seeing the patterns. Does that make sense? Yeah. Okay. So these are unsigned numbers. These are signed numbers. Please tell me that you are like. It's not super important, but how many people are familiar with like? Do you understand why -1 is FFF? Everyone understands 2's complement? Is anyone here that doesn't understand 2's complement? Don't be shy. Raise your hand. Okay, super quick, because I don't have a slide for this. Negative values, negative values pretty much everywhere. They are represented using what it's called. My handwriting is beautiful. 2's complement, which means that if you have value, it starts with 0. Like we are going to looking at the binary data, right? Like so, imagine that we have one byte, and this byte inside has 8 different flags, right? So if we look at 0, it will be 0, 0, 0, 0, 0, 0, 0. Right? Like these are different, the 8 different bits, right? Now, if you want to represent 5, right? So 5 is what? 1, right? 0, 1, 0, 0, 0, 0, 0. Yes? Like this is positive values. Now, what if we want to do -5? Right. So if we just use like there are different ways of representing positive and negative values. If one possible way is let's just use the bit at the most significant bit. It's called, this one is the one at the left, for expressing the sign, right? So if we did that, we could do this, and that will be -5, right? And that seems intuitive. It's like, okay, this flag kind of let us know whether it's a positive value or a negative value. The problem with this is there are two big problems with using that method. For the first one is that then we have two different zeros. We have -0 and +0. We don't want to have -0 because 0 is 0, right? And the other big problem is that when doing the XOR operation that does addition, this doesn't work. So to kind of fix those problems, there was this thing that was invented that I think is pretty cool. That's 2's complement, and it's the standard way of representing negative values in general. So if you wanna express 5 as -5, basically what you will do is like you will flip all these bits, right? Like you will do the opposite, and then you will add 1, and then that will give you the 2's complement value, which is if I recall correctly, is the same one as going. It will be -5 will be. I think it will be 1, 0, 1, 1, 1, 1, 1. So this will be -5. If you had 8, for instance, imagine that you have 8 and you want to do minus. No, that's not 8. Imagine that you have 8 and you want to convert this into -8 in 2's complement, right? So what you would do is like you will flip all these values. So 1, 1, 1, 1, 0, 1, 1, 1, and then you add 1. And basically, what ends up happening when you add 1 is that it becomes 0, 0, 0, 1, 0, 0, 0, 0. Yes. Yeah, but they do another trick, which is like you just keep this until you find 1, 1, and then you flip all the others, which is the same. It's exactly the same. So you go like that until you go from right to left until you find 1, 1. So you go from right to left, and you keep those intact. And when you find the first one, you leave that one, and the rest you flip it. So -8 in complement 2 will be 1, 1, 1, 1. These are bits, obviously, and then 1, 0, 0, 0. Right? So this is 2's complement. That's why. So, and then one of the nice properties about 2's complement is that on one end, in 1 byte, we can use all the possible permutations for all possible values, meaning that we can go from -128 to +128, right? Because if we didn't do that, then we'll be wasting at least -0 and 0, so that would be pretty bad. And the other one is that when we do mathematical operations at the CPU, we treat it like any other number, and it works out well. Like we do the XOR and for doing an addition, for instance, and it's the same. Yes, questions? I didn't explain this part very well, but like hopefully it's not super important because we're not going to be using. Yes.
So how would you know that's -8 and not just a really big positive number?
Because this is telling us.
Okay.
Yeah, like inside it, because if it's there are signed and unsigned values, right? Like we need to know if we're working with a signed or an unsigned value. If it's a signed value, the bit at the most significant bit is going to tell us if this is positive or this is negative. If it's 1, it's negative. If it's 0, it's positive. Yes? Sorry. I'm listening. Oh.
I have a question in the meantime.
Yeah, go ahead.
Okay, yeah, Adrian here. So this applies for little endian. Do I just believe that for big endian?
Hold on. Like 2's complement
Yes.
is orthogonal to endianness.
Okay.
because 2's complement works at like 2's complement is orthogonal.
Sure.
It's
But the leftmost bit is reserved for the negative
this
sign.
this one byte, right? Like remember that inside the byte there is no endianness inside the byte. These are the bits inside the byte.
Okay.
Does that make sense?
Yes. Okay.
Remember, endianness applies at the byte level. So it's
Yeah.
like I always talk about boxes inside the boxes. So like inside the box of the byte is where we have these bits, and 2's complement applies to the bits inside the byte.
So it doesn't matter if it's big endian or little endian. That space is reserved for indicating negative value for sign.
That is correct. Like
Okay.
basically like so. It's a good question. So minus one is going to always be the same in little endian and in big endian. Why? Because minus one is always going to be like all the bits one, so it doesn't matter, right? But minus two, for instance, right? Then what's going to happen? If it's a U8, well, if it's a U8, it's a U8. Like the endianness cannot apply to just one. But if it's a U16, yeah, then we're going to see it flip. Does that make sense?
Yeah, you're padding the zeros.
Mhm.
Okay.
Yeah.
Thank you.
Yeah. 2's complement is just a way to represent like the binary data behind it on each byte. Yeah. I was going to remove it. Are we done? Like I didn't want to spend too much time with this. I just want you to know that also we're not signed integers are rarely used in blockchain. Well, yeah, rarely used. But yeah, if you use them, then you should be familiar with 2's complement, right? So again, now that we know, in this example we can see clearly, right? Like, or for instance, this one is a better one, right? Like, check it out, right? Like minus 256, right? Like in little endian, the FF is here. In big endianness, it will be 2's complement 2, but the bytes will be flipped. Yeah. Let's go. Okay. Booleans. It's another basic primitive. We use 1 byte for expressing Booleans, which means that we're wasting 7 bits that are completely unused, such as life, and they get encoded and decoded like that. Yes. Julio. Okay. Scale. Scale is the coolest part of scale. Compact is the coolest part of scale. It's like it's this kind of very unique primitive that kind of is the flag signature of scale, if you want. Okay. So let's dig into it. It's a little bit. It's pretty cool. Okay. So scale is a primitive that allows us to optimally store any integer from 0 to 2 at power of 536 without wasting memory, or using memory in the most efficient way possible, right? So think about it. There are many times that we have to deal with a situation where we know that the value can potentially be very, 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 very big, but that most of the times it's going to be small. So what do? Do we reserve like a U256 wasting a lot of bytes when in reality most of the times we could be using less? So this is a little bit one of the problem that Compact solves. Like it can dynamically know how many bytes we have to use for each number. So the way that it works, this trick is like this. The 2 least significant bits of the first byte are going to tell us how many bytes we're going to use next. Because remember that in scale, everything is concatenated. And we have to know the definition beforehand. And as we decode, we know what's next, right? So we're about to decode compact. So when we decode the compact, we take the first byte, and out of the first byte, we look at the two least significant bits, right? Okay, so for instance, there are 4 different modes because these 2 bits are going to give us 4 different permutations. If these 2 bits are set to 0, it means that the value is self-contained in this byte, right? So we just read 1 byte. We know this is going to, we know that we're reading a compact value. And now, when we look into that byte, we look at the 2 least significant bits. If they are set to 0, that means that we need to use the other 6 bits of this byte to read the value. That means that in this modality, we can only have values, we can only express from 0 to 63, meaning that if the number is more than 64, we're only going to be using 1 byte. Awesome. If the flag is set to 1, by the way, this 0b here, remember that before we explained that like there's this convention that is 0x. There's another one, maybe not so known, that is 0b is a convention for saying that what comes next is expressed in base 2. It's like zeros and ones, okay? So if it's set to 1, if the flag is set to 1, it means that we're going to be using 2 bytes. The byte that we're currently reading and the next one, right? So we can express up to 14 because we have 6 bits in this byte plus the 8 bytes of the next one. That's 14. That's 14 bits, right, in total. So this is the maximum value that we can express in this mode. The third mode, it's telling us, hey, again, you're using 4 bytes, like the byte that you're reading plus the next 3 that come afterwards. And last, but the most powerful one, is when it's set to 3. When these 2 bits are set to 1, 1, or they are both set, then what this is telling us is the remainder 6 bits of this byte that you're reading are going to tell us how many more bytes are you going to need to read, right? So if it ends with 1, 1, we're going to take these 6 bits that we have, and we're going to compute, we're going to see, like, okay, how many bytes are they telling us? And to the number that they give us, we're going to add it 4, right? So that's why compact allows us to express, to use a lot of bytes when we need them, and very few when we don't need them. So if the number is very small, we're going to be using just 1 byte. If the number is very large, we're going to be using an insane amount of bytes. Does that make sense? Let's see some examples, because this is it's a little bit complex. Okay, so how do we... Okay, so let's encode together 1 as a compact value. So these are bits, right? So we only need 1 byte, right? Because it's less than 64. So these 2 bits, we set them to 0 to indicate that it's in mode 0, like we only need 1 byte. And then in the remainder 6 bits that we have, we set it to 1, right? Therefore, this is in hexadecimal. Who can tell me what this is in hexadecimal? No one? For real? Oh my gosh. 04, right? Like this is 4, right? Like this is 0, this is 2, this is 4. So this is 4. So what about 2? 2 in hexadecimal is nice. And 3? What would be 3? I don't have 3
I'm
here.
sorry.
Oh yeah, no, I actually have 3. Okay, I have 3.
Okay, so this one will be, I believe, D.
C.
C. Okay.
Yeah,
C.
close enough. Like the basically is 12. So one thing to notice is that, as you can see, like 1, 2, 3, like it's like one cheeky way to increase. Like they keep going like 4 plus 4 plus 4. Why? Because these 2 bits are taken. So in order to increase it by respecting those 2 bits, the next value is going to be 4 plus 4 plus 4. It's going to be a power of 4 for variant 0. So, and so on and so forth. So like C is 12, right? Ergo, the next one, like I don't have 4 here, but 4 will be 0x10 because it's 16, right? But anyways, like, so, but you see the point, right? Like in scale, we look at the first byte, and the first byte is telling us, hey, we look at these bits, it's like, you only need to use this byte. Then we look at the rest of these ones, and they are telling us, these are 3, and we express it like that in hexadecimal. 63, obviously, is the maximum that we can have in this mode 0, which is expressed like that. What about 64? So for 64, as you can see, we don't have enough bits here. So we need to move to the next variant, which is saying like, hey, you need to use the next byte. So in hexadecimal, that will be 0, 1, 0, 1. So because scale is concatenated, remember, like we start reading the first byte, and when we read the first byte, it's like, aha, I need to use the next one. We go, we read the next one, we compute it, and it gives us 64. Yeah? 65, who can tell me, who can guess how 65 is expressed in hexadecimal, taking into account that this is 64? What will that be?
0501.
0, what?
05.
5.
Yeah, 0501.
Yes. Okay, a little exercise for you.
Sure. He has a question.
Oh, yes.
Sorry. I guess I didn't quite understand like the first example because I thought like the last 2 significant, like the least significant digits just represented how many bits it was taking or how many bytes it was taking, and then everything after that just read normally. So why wouldn't the first example just be 0x01? I'm a bit confused.
Sorry, what's confusing?
So I understand that the last 2 byte, like the last,
The last 2
bits,
bits.
the last 2 bits, yeah, yeah. So
of
that
the first
represents
byte. The least significant bits of the first byte, yes, are flags letting us know the mode, and there are 4 modes. Let's go back 1 second. There are like these 4 modes, right? Like when the last two bits are set to 0, they are telling us just use the other bits in this same byte. Does that make sense?
yeah, like the 6 digits before it, right?
The what?
Oh, sorry. Okay, maybe I didn't understand. Okay, can you explain that again? So just use what?
Let's recap because this is important. Okay, so scale, compact. So remember, scale is concatenated, right? Like, so we read bytes, and as we read, they are telling us what we need to do next, right? So we read the first byte. When we read the first byte, we look at the last 2 bits of that first byte, yeah? And there are 4 different permutations, 0, 1, 2, 3, yeah? If the permutation is 0, what it's telling us is like, you don't need to look any farther. Just like the value is self-contained in this byte, right? And for that, you have to use the remainder 6 bits that you have, yeah? Therefore, in mode 0, we can express up until 63, because there are 2 bits that are being used for the flag. We cannot reuse them for the value of the number, right? If it ends with 0, 1, it's like, oh, on top of this byte, you need to use the next one. But obviously, in the next one, there are no flags anymore, right? So for the next one, we can use the 8 bits in there, right? So in total, we have 6 bits available in the first byte and 8 bits in the next one. Total, we have 14 bits. So the maximum value is 2 power 14. Mode 4 tells us that we need to use 4 bytes, right? Like it goes like, okay, we need to use 4 bytes, same deal. And the last mode, this is mode 2, sorry. And mode 3, like, or depends how you look at it. When the 2 flags are being set, what this is telling us is like, okay, like the 6 bits that you have in here, the 6 bits that were for the value, they are going to tell you the number of bytes that you need to grab plus 4, right? Okay, so at first I was showing just like the basic example. Like, how do we encode 1, right? Well, 1 fits in 1 byte, so the last 2 bits are set to 0, and then in these 6 bits we put the 1. We're done. Like this in hexadecimal is 4, 0, 4, yeah? What about 2? Well, 2 is this one here. So in hexadecimal, that's 8. 3 in hexadecimal is 12. Well, it's C is 12, basically, yeah? Because it's this guy, yeah?
Okay, I understand now.
63,
Yeah.
yeah. What about 65? So for 65, 65 doesn't fit in here. So we're going to need 1 extra byte. Therefore, the
Repeat the
flag is
0,
going
1.
to be set to 0, 1, letting us know, hey, go look at the next byte too, right? So it's set to 1, and then all this is 0, and this one is 1. Because remember, little endian. Does that make sense?
Yeah. For some reason I was separating the first 6 bits and the last 2 bits, and I wasn't realizing that you made them all into the same number.
Okay. No, it's good that we go through it again. Like it doesn't, but like, you see, in this case, like this is 64, like as a compact value, the compact value 64 is 0101, yeah? And 65 is, who can tell me what 65 is? We just saw it, someone said before. Thank you. Okay, so now I want you to do an exercise. Like, don't use AI, you can use a computer if you want, but don't use a library, like you have 5 minutes tops to solve this. But try to manually decode with what you've learned. Try to decode these two things. Yes.
Hi, sit here. So the first 2 bits will always store information about how much the system has to read. So unless the information itself is less than like 2 bits, I'm always, this is an edge case where I'm always wasting 2 bits to tell the system that, okay, you have to read these 2 bits. So in that case, scale encoding is always like, has more memory usage than just normal. So my first 2 bits, like the least significant bits, will always contain information about the actual data that I want to send, right? So unless it's like more than 2 bits, the actual information, I'm going to waste like 2 bits of my memory to tell the system, okay, you have to only read this much. Is that right? Understanding then? Like this is an edge case we are talking about?
Sure. I mean, like, so if you have the guarantee that the value that you're going to read will always be less than 256, then don't use compact, use a U8, right? But if you don't have that guarantee, right? In some cases, it makes sense to use compact. Because if it's going to be a variable number, most of the times when it's small, you're going to use, so yes, I guess the point you're trying to make is that we're investing 2 bits for expressing how many bytes we're going to use, and in some cases, because of these 2 bits, we end up using more. Yes, in some cases, if the number is very small, yes.
Yeah, just I want to point an example that to me was clarifying. Is that, for example, when you want to set a counter, so for example, how many accounts do I have in my application or whatever? This is a good fit for compact because you know that numbers are preferably small. So you start by 1, 2, 3, 4, and let's say you want to have at max, I don't know, 2 million accounts or whatever. Then you don't need to reserve the whole memory that makes it fit 2 million. You can use compact so that in the early stages, the number is small, right? Does that make sense?
Yeah, so if the allocation is very big, but the realistic
Exactly.
numbers are small, then I can always use this.
Exactly, because it's preferably, the numbers are preferably small.
Okay, so
Make
like
sense?
account balance, so,
A balance, for example, is a good fit as well.
We'll see a more concrete example. Like when we look at the complex types of scale, we will get into vectors. And vectors, I'm already like giving you a spoiler alert. Vectors, the first byte, the first bytes are going to let us know the length, right? So most of the time, the length of a vector is not that big. Sometimes it's very, very it's very long, right? Because sometimes we're expressing vectors of bytes, or sometimes we're expressing vectors of complex things. So most of the times, the dynamic number of elements is small. That's why compact is very useful, because we use just a few bytes. Overall, we'll be saving a lot of memory, right? Okay, so
the guy in the front.
have you guys
Josep.
had time? Have you guys and girls room? Everyone.
There are two more questions.
Yes,
The guy in
yes.
the front.
How do we get the maximum number? Why is it two power of 536?
Go again.
How do we get the maximum number? Why is the two power of 536?
Oh, the maximum number.
Yes.
Because
Why is
Yeah.
536?
yeah. So the maximum number. Let's think about it, right? The maximum number is in this mode. This mode is telling us, use the remainder 6 bits of this byte to let you know how many bytes we have, right? Okay. So if the 6 bits are set, right? Plus 4, yeah? So the question is, let's do it. Let's work it together, yeah? It's 1, 1, 1, 1, 1, 1, 1, 1. So this is for the byte. Now, this is 63. This is 63, right? Now it's 63 plus 4. Plus 4. Okay, so 63 plus 4 equals 67. So 67 times 8, because we are looking at the bits, is whatever. But you will realize that 67 times 8 is 2 at the power of 67 times 8 minus 1 is that. Does that make sense?
Yes.
So the maximum number of bytes that compact can tell us to use for a number is 67, which is insane. Like it really is insane. Like I've never seen anything. I mean, normally, very rarely you will need to use something above U to 56, right? So, but yeah, like that's how you get the maximum one. Does that make sense?
Last one.
Hi, I'm Naren. That still leads to a max of 2 to the power of 5 and 2, right? And not 2 to the power of 5, 6, 3, or 5, whatever number it was.
Sorry, what? What was that?
Even if we use the whole byte for representing the length of, how much are we using, how many bytes are we using, it leads to what? If all the bits are turned on, all the 6 bits are turned on, that will say we have 64 bytes, which effectively leads to up to 64 plus 1, that's 65 bytes usage, right? It's not 2 to the power of 536. It will be 2 to the power of 5 and 2, isn't it?
No, it's not right. The thing is that there's a trick, and the last mode that was the last mode tells us to read the length. So the maxi in the rest of the byte. So the maximum length that we can read is 63, but we do +4 because we already know that if the answer was in, so if the number fits in 4 bytes, we would be using the mode above. So we add 4 bytes to the length. So it's 67 actually.
Yeah, I
Is that
already
right?
explained that. Yeah.
How do we get 67?
So the thing is that that we can encode 63 in 6 bits, right? So the maximum length that we can encode is 63 bytes, but we add 4 as well because if
Or we use even those 2 bits.
So in mode 4, which is like with the bytes, it's so this one is telling us use this byte. This one is telling us this byte and the next one. This one is telling us this byte and the next 3. And this one is telling us, okay, the rest 6 bits are going to tell you how many bytes you need to get. +4. Why? Because there is this here. Like it's too big, it's less. That's why I mentioned +4. Yeah. Anyways, like, can we? Yes. Has anyone solved the problem that I gave you manually?
Yes. But I have a question. So you can take 4 bytes in 2 cases when you have.
No. That's what
no.
we're going to see in a moment. No, you
Okay,
cannot.
Okay.
No, you cannot. I know you're going. No, you cannot. That's the trick here. Yeah. Okay. So who can solve that? But that's a really good question. Okay. So who can solve these two? How do we decode this as compact?
So can I say the answer? So
Yeah,
the first one is 16,320 because it's like 255 times 63, I believe, or 64 times 64.
This is how there are 1,000 ways of doing it. This is how I will have done it because I'm mostly a JavaScript developer. This is how I will have solved this if it was up to me. And maybe I will mess up, but like I will have done 0x ff 0 2. Is this your result? Yeah. Okay. So this is what did I do here? It's like, okay, I pass it to big endian, and then there are 2 bits that I don't want out. Basically, it's like but there are 1,000 ways of doing it, right? But yes, if you got this number, you got it right. This is the right answer. Now, what about this one? Who has been able to decode this one as a compact? You?
So the other one is, I believe, 1.
No. This is a trap. This value is, if you try to decode that as a compact, you're going to get a panic, you're going to get a throw, you're going to get something bad, because that is not a valid compact value. And this is something that is very important, and it's related to what he was saying before, which is that certain permutations with compact are not valid. Why? Because of what we explained here. Okay, so why is this one not valid? Because here, this 0.5, what this is telling us is this. It's telling us it's like we're using just 1 byte, right? Like there's nothing else. There's no more memory, right? And this 0.5 is 1, 0, 1, 0, and 4, right? Like this is 5, right? So, okay, this flag is telling us, what is this telling us? Is you need to use the next byte. But where is the next byte? It's not here. So when we try to get the next byte, what's going to happen? Like if it's rusty, we're going to get a panic. If we're, yes? What?
What if you fill it and add zeros at the end? It's still 1?
At the end of what?
At the end of this, if you add another byte,
Well, if you have another byte,
But
then,
yeah,
then
yeah,
it's
but-
a different story.
but-
Yes. So 0500 is a valid compact value. This is a valid compact value. Yes. Well, oh, no. It's still not because it will. The reason. No. It's not. It's not. The reason why it's not. Hold on a second. No. 0500 is also not a valid compact value. Why not? Because the value that it's trying to convey fits in just 1 byte. So it's not. That's not the proper way of encoding it, right? Like even if the byte is there, even if we put it these 2 zeros, this will still not be a valid compact value. Because sure, we'll grab the next byte, but this is not the right way of expressing it because of its own value. The point that I'm trying to convey here is that not all possible binary permutations are valid compact values, right? Precisely because of the nature of this, right? Does that make sense? In the same way that you could a more concrete. Yes, this is actually a very good example because here we have 1, right? And it's little endian, so it's already here. So if we just put zeros, no, like because it's 1. For 1, the flag should be 0. Yes? So yeah, that was like, I did that on purpose just to convey the point that in compact, not all permutations are valid. Does that make sense? Question, sorry?
So does that apply to all odd numbers under 64?
Go again?
Is that true then, as in not valid for all odd numbers under 64?
I can understand you, sorry.
Like 5 is an odd number under 64. Does this problem apply to all odd numbers under 64?
Yes, I guess.
Not just 5, but 7, 9, 11.
Yeah. The point is like there are many, yeah. Yeah. So shall we take a break? Quedan 20 minutes. All right, let's speed it up. Okay, so complex types. Complex types are complex types. Until now, we've seen like the primitives, right? Like so, unsigned numbers, signed numbers, booleans, and compact. Compact is like this very powerful primitive. Now let's see the complex types. There are tuples, simply a concatenation of different types of codecs. So a complex type is basically a codec. It's a type that references other types, right? Tuples, structs, vectors, arrays. A vector is when the size is dynamic. An array is when the size is static. An enum, we'll see them at dev in a moment if we have time. An enum is a discriminated union, and then we have what I call specialized enums, which are like specialized tag unions. One is option, and the other one is result. And then specialized vector and opaque, which are kind of meta complex types. Not that important for now. Let's move on. Okay. The enum. The enum is a complex type in which we express, for instance, we express enum, and it's like, okay, an enum where like the tag foo is a U16, the tag bar is a Boolean, and the tag bast is nothing. So it's just like bast. So the first byte is going to tell us which variant are we going to read next. So if the first byte is telling us it's 0, if the first tag is 0, we know that we have to read 2 bytes next, which are a U16. If the tag is 1, then we need to read 1 byte, which is going to be a Boolean. If the tag is 2, like if the value of the first byte is 2, we don't need to read anything else because it's just bus, right? So An enum or a tag union is this complex type that it's very cool because it allows us to, it's like, okay, now you need to decode, you're going to, this variant is the winning one. This is the value that comes, and then as we read it, we know what we need to decode. Okay, so let's see some examples for this. Let's imagine that we are that we're trying to decode this value. So in this case, this will be this 0 here. Sorry. This 0 here is the one letting us know that we need to read 4 bytes, and these 4 bytes are for 1. This is the same thing for, this is telling us, okay, this is a 1, so it's bar, so the next byte is a Boolean, which is false, and this one is just, okay, there's nothing else here, so, and it's 2, so it's fast, yeah? Some observations about enums. Enums make it possible to have circular codec definitions. So we can have some codecs that have circular references between them, but because if they're expressed in an enum, the enum can break the circularity eventually, right? So you could have an enum where one of the inner variants is a vector of that same enum, but there's going to always be a variant that is going to break that circularity, right? So enums, among other things, make it possible to have circular type definitions. Otherwise, we wouldn't be able to because we wouldn't be able to get off the site. Another observation is that the result and option are two special types. An option is basically telling us whether there is a value or not. If the is set to 0, it means like there is nothing else for you to read. And if each one is like that value, it's present. And a result is basically a type for when things go well and a type for when things don't go well. These are just specialized enums. They are still tag unions, variants, whatever you want to call it. And the other observation is that because the first byte is the one that indicates it's the flag that indicates which variant we're going to be using, there cannot be more than 256 options, unless we do some tricks with like, you could have some sort of convention that's like, oh, if I need more than 256, then I'm going to use FF, I'm going to use 255 as I'm going to do a nested enum in there. Unless you do something like that, an enum cannot express in its own more than 256 options, okay? Okay, this, I already explained this. An option is a specialized enum where 0 means that there is no value, 1 there is a value. So if we have an option of a U16 and we read 0, that means it is null because it's 0, like, so there's nothing here. An option of U16 where it's set to 1, this is, what does this decode to? An option of U16 to this, what does this decode to? Who can tell me what this is? Number? Number 1? For sure. 256, because it's little endian. You see? Little endian always tricks us. Yeah, like that's the whole point. Like we start reading, and then here it looks like it's going to be 1, but if you think about it, it goes like that, and it becomes 256. Okay, result. Result is a specialized kind of variant where 0 means that it went well, and 1 means that it didn't go well. So we can have a result that's like, okay, when it goes well, it's a Boolean, and when it's an error, it's a U8. I'm going to move fast because it's just a specialized thing. It's more of the same, and we don't have a lot of time. Okay, the structs and tuples. The structs and tuples are conceptually the exact same thing. Because remember, for scale is not self-describing. So you need to know upfront the types that you're reading. So a struct and a tuple, it is the same, but with structs, the fields have labels, they have names. And in a tuple, they don't. Like, by index what they are, but they don't. So for example, these two things, this tuple of tuples, right? And this struct are going to produce the same output and that they're going to produce the same binary data. It's just that when it decodes, one is going to decode with name labels in the fields, and the other one it won't. Okay, so let's do a quick exercise together. Let's decode this. Let's decode this struct. So just so that we see that it's just concatenation, let's decode this struct together. Okay. So this FF belongs to what? To the color red, right? So this means that red is going to be 256, green is going to be 0, blue is going to be 16. Is it going to be ready? Yes. Its Boolean is going to be true. And then the price, which is an option, it's set to true, so the value is there. So we're going to read the next 2 bytes, because it's a U16, and that's going to produce the value 256. Yeah, it decodes like that. Another example, it goes like this. I wanted to show, we're very short on time. I'm not going to, okay. Vectors. Vectors is another complex type, and now here we can see one of the places where compact is actually very useful. A vector is a complex type where the encoded value, so the first thing that we read is the number of instances that we're going to find, right? So for example, a vector of U8, this is just bytes, right? If it's an empty vector, what is it going to be? 0. If it's a vector with one item, what is it going to be? The first byte is 04, and then is 0401, but it's correct. Like the first byte is telling us the length, which is 04, and then we have the value inside, which is 01. Yes, it's 04 because remember, it's compact encoded, so in compact encoded, one was. Now, 2, remember 2, it was 08, because we go 4 by 4, so it's 08, yeah? And then we have 2 values, which are 01 and 0, yeah? So this goes like that. Okay, let's make it funner. We can also have a vector of compacts. Like this one was easier because it was just like, what about the vector of compacts? We can have a vector of a vector of a vector of a vector. Like we could have these are complex types, right? But let's see a vector of compacts. Let's see if we can decode them. Okay. So how is it going to be encoded? There are 2 elements, which means that it will start with 08, right? And then what are we going to find? 04 and 0. 08, 04, 0. Yes? Does that make sense? And last but not least, let's try it. 3 is 12, which is C, 0C, 0C, 01, 00, and oh, no, it's compact. Sorry. All right, we don't have too much time to think about it, but like, yes, 0C is telling us that there are 3, 04 is 1, 00, and 64 is 0101. Arrays are when the length is known when the length is known at compile time, then we don't need to read the size first. Like we just put it there, right? So in that case, these ones are a lot easier. It's basically like a tuple of the same thing, but with the length of it known beforehand, basically. So here are a few examples of how to encode and decode arrays. Like it's basically like vector, but without the compact at the beginning, because the one who is reading already knows how many iterations of that type go in there. Yep. Okay, and maybe we'll have time to 5 minutes. Okay, so quedan 5 minutos, intento acabar OP. All right, so am I going too fast? Was that clear? More or less? Yeah? Okay. Opaque. Opaque is kind of so sometimes, remember, like with scale, one thing that you may have noticed is that we have to always go in order to decode. So we need to decode everything. So sometimes we want to be like, hey, like the next n bytes, please keep them. And inside these n bytes, maybe we know that it's scale encoded data, but you don't need to decode it because it's for someone else or for later evaluation, right? That's when we use opaque. Opaque is basically a way of saying, for instance, the body of a block, right, is a vector of opaque extrinsic. So what does that mean? Extrinsic is a codec that is a quite complex codec that it generates some binary data. But many times the node is not interested in decoding this extrinsic because it's the runtime that will actually apply it. So when it imports it, it's going to import it as opaque. There's going to be a vector. There's going to be a vector of opaque extrinsic. So basically, opaque means that there's going to be a compact value that is going to tell us how many bytes come next that need to be treated as a blob of binary data, right? Even if this blob of binary data is actually a scale encoded, but for someone else to deal with, right? So a good example is the block of the body. There are other examples like metadata. It's just quite a bit. Yeah. And then it turns out that I went too fast. And then here we have some implementations of, if you want to use it with your favorite programming languages, these are some implementations of scale encoders and decoders. Okay. This the most important one is the one from Parity for Rust, because scale is mostly thought for Rust for sure. There's one pretty cool one for TypeScript that we use it. And then I also want to show you some tools that you can use to fiddle around and kind of learn a bit more about scale. So the first thing is like, if you go to the Puppy Dev console, right? And you try to create an extrinsic or whatever, we'll talk about like where the encoders and decoders for these things are when we talk about the metadata. But like if you do like oh, sorry. What, oh. What in the world? It's not picking it up. Sorry, 1 second. One thing that you can see here is that one cool thing that you can see in the DevTools of PAPI is that whenever there is a scale encoded data, as you hover the different values here, it highlights each part of it. How is it what is it in the binary data? There is this other tool. It's very alpha, but it's scale.papi-how. And then in here you can use it for trying different things. And you put a compact value here, and then you see it here. You can put a variant here. So you can create your own little definitions in here. And you see, this is telling us, oh, this is not good because we set that it was an I16. So if it had been a U16 instead, that would have been a valid value. And then, what? I'm in U8. Ouch.
Joseph, we need to wrap up now.
Okay.
That's okay.
So try it on your own with scale.papi-how. Thank you for your time. I hope this was useful.